Thanks. I'll begin with a prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray you be with us today. Help us to, again, Lord, glorify you in whatever we do, Lord. In your name I pray. Amen. Is the audio, is it bouncing? Okay, cool. So I just gave you guys a supplemental homework. Basically, this is to try to draw your attention to the things I've said in lecture but are not really in the book homework, but I do still care about. And so this will be due Tuesday, along with the rest of the homework. Yep. Oh, I'm sorry. I somehow missed you when I looked at that row, and I know it's somewhat ironic since you're the only one who asked for one. So basically here, there's just a couple of elementary questions about path, position, well, rather the path, the velocity, the acceleration, the colliding tangent line, and then just basic dot product stuff. So let me just kind of give you a lightning tour of some example problems. First of all, A dot B is equal to, oh, I see this is going to be an issue. So here's the homework I'm going to put back here. Just take one. Thank you. So if we look at A dot B, by definition, it was A1B1 plus A2B2, all right? So my first example, here's two vectors. Find their magnitude. In other words, find their length and find the angle between them using the dot product. So to find their magnitude, I just take the square root of the sums of the square, like 3 squared plus 7 squared, square root that gives me square root of 58. That's the length of A. Length of B is square root of 2. But then A dot B I can calculate. Well, that's minus 3 plus 7, otherwise known as 4. Now there's a theorem. The theorem says that A dot B is also equal to AB cosine theta. So AB cosine theta, AB cosine theta I can solve for cosine theta because I know 4 and I know AB. The symbol without the vector is understood to be the magnitude here, okay? So there you go. Cosine theta is 4 over AB, which is 4 over the square root of 58 times 2, square root of 2, which, by the way, is 4 over the square root of 116. You could simplify, but who cares? Anyway, the point is, inverse cosine of this quantity is 68.2 degrees. And so there you have it. The angle between the vectors is about 68.2 degrees using the dot product technique. Yep.
What's up with using inequalities as brackets?
Oh, this is a usual notation for vectors. I'm not usually using it in here, but I do everywhere else. I mean, I allow myself to add these and those. These I think of as a directed line segment, whereas these I usually think of as points. But there's always this correspondence between a point and a directed line segment. So, as to make the question not be asked, there we go. Okay. Sorry, I will try not to do that other thing in here. Don't read too much into it. This we'll come back to. My next example, I look at the derivative of a function of time times a vector of functions, all right? So the scalar multiple of f times a is equal to fa1, fa2, because that's what A is A1, A2. Now, I'm thinking of f and of a. Everything here is just arbitrary functions. So I'm showing you how we can derive a property of the of the differentiation of a vector. So what you do is, by definition, the derivative of this is the derivative of the first component, comma, the derivative of the second component, right? But this is a product of functions. That's a product of functions, so I have to do the product rule, like so and so. Then you notice that there's two terms that have df dt, right? And so I can rewrite this as the sum of these two vectors, this vector plus that vector, all right? And then you notice that you've got a common scalar multiple of df dt, so I can pull that out. Got a common scalar multiple of f here, so I can pull that out. And so there you have it. I've got df dt times a plus f times dA dt. This calculation I'm showing you, the reason I'm showing you that is because I've asked you a very similar question in this homework I just gave you. Problem number 6, I asked you to show the product rule for the dot product, all right? And the product rule for the dot product is shown in much the same fashion. You just have to do the product rule on, an arbitrary, basically you have to do the product rule on this and then regroup terms, but it's kind of similar, the spirit of the calculation. So I'm hopeful that this example helps you see how to do problem 6 and the thing I just gave you. This much I can tell you, don't make up examples and show me it works. I'm asking you to show it in general. You have to work with arbitrary A1, A2, B1, B2, okay? This is another example. Here's a path, sine of t squared, e to the cosine t plus t. This is kind of awful. I think the one I gave you in the homework, which I have inconveniently left back there, is simpler. But anyway, let's work through this one. And so find the velocity, find the acceleration, and also find the colliding tangent line at t equals to 3. The earlier section forced 3 upon me, so we're stuck with it. It's not pretty, but it's not too bad either. All right, so first of all, the velocity. How do you find the velocity of a path? You differentiate, right? Derivative of x dt, comma derivative of dy dt, which is just this and this. But here I got to do chain rule, 2t cosine t squared. Over here, minus sine t e to the cosine t plus 1. So there you go. That's the velocity at time t. So I'm ignoring the wording of the question and doing something asynchronous. The next move I would make logically is to write down the colliding tangent line, because I have everything I need to do it now. All right? By the way, if you look in my notes and stuff, you won't find the terminology colliding tangent line. That's something I made up just this semester just for you guys. And I like it, and I'm going to keep using it. So if you're looking for colliding tangent line in the notes that I've posted, you won't find it. I just talk about tangent lines there, and I don't usually care about recentering it so that the parameter of the tangent line matches up with the parameter of the given path. It's colliding because R of 3 and L of 3 are both at the same point, So at the same parameter, the tangent line and the path go whoop, and then so. Anyway, bottom line, you plug in time 3 into the path, you plug in time 3 into the velocity, and you form this linear combination like so. It is very important in this problem that you take the time in the velocity and you replace it with the appropriate parameter, in this case 3. Leaving velocity as a function of time here does not give you a tangent line. It gives you something else, which is wrong. Very, very wrong. But also very popular in tests, both in here and in Calculus 1. In Calculus 1, the popular mistake is, well, let me not show you, but usually people ask them to find the tangent line, right? They'll calculate dy dx equals to like 3x squared, and then they'll write down the tangent line, and they'll put 3x squared for the slope. But what they're supposed to do for the given question is to plug a value for x into the 3x squared and get a number for the slope, all right? In the same sense here, this v of 3 should be a specific direction vector. It should be a pair of numbers, a vector, a direction vector, okay? It's a pair of numbers for a given specific tangent line. It doesn't have to be pretty, 6 cosine of 9, comma, minus the sine of 3, e to the cosine 3 plus 1, but nevertheless, it is a specific set of numbers, albeit these are ugly because they put me at t equals to 3. Any questions about the red? Yes, sir? I just need something other than R of t, because R of t has a meaning, so I need something else. I don't really have a privileged notation, but I tend to use L of t for the tangent line, yeah.
So that's the equation for the tangent line?
At 3, yeah, which is colliding. If you don't care about colliding, all it means is I might erase this t minus 3 and I just put t. That's all. But then the parameter line, the parameterization of the tangent line has the point of tangency at t equals to 0, whereas the path gets to that point of tangency at t equals to 3. And so then they wouldn't be colliding, they'd just be intersecting. And you have a variety of other flavor choices. I mean, there's infinitely many different parameterizations for that line. So I'm just describing 2 at the moment. Some of you will soon take Calculus 3. Well, after a summer, probably, possibly not, I don't know. When you do that, a lot of times you'll be looking at tangent lines where you're just trying to gain some geometric information from it, you know. If you're doing that, there's really no need to put the t minus 3. A lot of times you could just put t there and get what you need from it. Just saying. But anyway, okay, so next, the acceleration is dv dt, so you differentiate this and that with respect to time. Product rule, chain rules galore, and there you go. 2 cosine t squared, 2 cosine of t squared minus 4t squared sine t squared minus cosine of t e to the cosine t plus sine squared e to the cosine t. There it is. There's the acceleration. Pleasant? No, but easy? I would argue yes. Yep.
So the blue is the velocity equation, and black got all the way to the side of the acceleration.
Yeah, this is the acceleration. Acceleration is the derivative of the velocity. So we have to differentiate both of these with respect to time, which... Now, I didn't ask for it in the original problem statement, but I thought, while I'm at it, let me tell you, if you wanted to calculate the arc length from t equals 0 to t equals to 3, what would you do? You would integrate the speed from 0 to 3, right? What is the speed? The speed is the magnitude of the velocity, right? It's the length of this here vector. So to calculate arc length, I would do the square root of 4t squared, cosine squared t squared plus this stuff squared, 1 minus sine t e to the cosine t quantity squared dt. Now, I wouldn't recommend that you try to do that integral. I don't like my chances for doing that integral. I will just say that this is an integral solution for the arc length. Much like you're asked for integral representations of the area in section 10.4. Kind of the same animal, right? Sometimes we like to ask you to set up an integral, but we don't want to actually make you do it. You know? Yeah. Hopefully you have gained enough comfort with integrals that you realize that writing the answer in terms of an integral is still a pretty significant accomplishment, because we have all kinds of numerical techniques to actually approximate this, right? Left sums, right sum, midpoint sums, Simpson's rule, trapezoid rule, all kinds of stuff. Wolfram alpha. Let's be honest. All right. My next example, this one, which I have erased the solution to, it's kind of backwards. I say, here's the acceleration. The acceleration is 1 comma t. And I tell you that the initial position is 1, 2, and the initial velocity is 6, 7. Then the question is, find a path with this data. This question's upside down from this one. This one, I give you the path and ask you to find the velocity and acceleration. This one, I'm saying, here's the acceleration, find the velocity and the position. Or find the parameterization ultimately, right? So how do you do that? What's that? You integrate, exactly. That's what I wanted to hear. So to start with, I've got dv dt equals 1 comma t. So integrating gives me what? V of t, some constant. And then let's see here, this gives me t. Integral of t is what? 1/2 t squared, right? But v of 0 is 6, 7, which is also equal to c plus 0, 0, right? So consequently, the velocity as a function of time is exactly 6 plus t, comma, 7 plus 1/2 t squared. Adding the c into the other thing. This marker's worthless. Okay, then how do you find the path then? Well, v, yes, sir. Yeah, so this c is equal to 6 comma 7, and that means this follows. Just because I just add 6, 7 to this, which is like adding 6 to the first component, adding 7 to the second component. Once I have that, right? Is that clear? Okay, so v is equal to dr dt, right? So dr dt is equal to 6 plus t, 7 plus 1/2 t squared. So what you can do, another way to do this calculation is to integrate, right? So R of t is equal to, well, 6t plus 1/2 t squared plus, let's say, b1, comma 7t plus 1/2 t squared plus b2. You see, you got options. I mean, you can either look at the calculation in terms of adding a constant vector off to the side like that, or you could think about adding a different constant in each component. Either way, you're doing the same thing logically. You got choices. You could either look at it one way or the other. Yeah.
Is this 1/6 to the third power?
Oh, thank you. Yes. Now you're making me doubt my other life choices. No, it's okay. It's okay. I actually did have that right in the earlier section. Believe it or not, I did. Somehow. To show you that you can do it two different ways. Sometimes writing the vector off to the side is more productive. Sometimes this is more productive. I just want to show you could do it either way. All right. And R of 0, I mean, I like to confuse the students, so if I can, I'll work on that here. R of 0 is, what is it? Well, it's on the one hand, it's given to be 1, 2, right? But on the other hand, it's also equal to 0 plus b1, right? 0 plus b2, so to speak. In other words, b1 is equal to 1 and b2 is equal to 2. And therefore, the path that we're looking for is exactly 1 plus 6t plus 1/2 t squared, comma 2 plus 7t plus 1/6 t cubed. You're like, why did you write the 1 and 2 first and not last? I don't know. There are many things I can't explain to you. But these are options. I mean, it's a polynomial. You can write the terms in any order you like. So I just chose that way for the answer. Again, in the interest of confusing the students. Ultimately my goal. Did it work? Okay. Thank you. Okay, I mean, kidding aside, does this make sense? So to find the path, we integrate the velocity, and then you have to apply initial conditions here because you're going the other direction. Yes, sir?
So the path is coordinates of R as
Yeah, the path is the parameterization for the curve. Now, physically speaking, it's the position of the particle. But yeah, when I say path, I'm talking about a parameterization. You should have a very strong sense of deja vu about this whole thing, right? Like Calculus 1, we do this. Except we just do one dimension, right? So you have a position function, you differentiate it, you get a velocity function, you differentiate it again, you get an acceleration function, and vice versa, right? There's usually a section on initial value problems before you even do the fundamental theorem of calculus. A lot of textbooks have this intermediate initial value problems where they give you like velocity as a function of time and ask you to find the position by anti-differentiation and then setting an initial condition, right? A lot of you should have seen that. And this is really nothing more than that, except what? We have two components rather than just one. But otherwise, it's the same song and dance. To get from position to velocity, we differentiate. To get velocity from acceleration, we differentiate, and vice versa. To get from acceleration to velocity, we integrate once. To get to the position or to the path, and as we also call it here, integrate again. And of course, when you integrate, you add constants, right? And so you can only resolve those ambiguities if you're given initial data, an initial position, initial velocity, as I gave you here. So there's that. Any questions? I mean, that good? I hope so. I think you should be able to do the problems that I gave you in the sheet with this. And finally, one last example to help you along your way on the supplementary homework. This example here is really just kind of a more grown-up version of what we've already done. We've done things like this before, but not quite this complicated, right? So here I've got x squared plus 6x plus 7y squared equals to 3. I say parameterize this curve for y less than 0 in the counterclockwise direction. So the first thing I'm going to do in a problem like this is I'm going to complete the square so that the true nature of the conic section can be revealed. Right? Completing the square shows me proof positive. In fact, this is an ellipse. It's shifted, right? Its center is minus 3, 0, but it's an ellipse. And so I divide by 12 to get 1 here, so it's like this, right? And then my thought process is, okay, so if I can make this thing cosine squared, right? If I can make this thing sine squared, t, then I'll have cosine squared plus sine squared equals to 1. I'll have a legitimate parameterization for this curve. Does that make sense? I mean, this was the logic we used before. It's a logic which is born from our understanding, in fact, our love of trigonometric identities. Dare I say. Yes?
How'd you get x plus 3?
I completed the square. So half of 6 is 3. So x plus 3 squared gives me back x squared plus 6x. But also plus 9, so I have to subtract 9 to be fair. So like these two terms right here are straight up x squared plus 6x, right? That's where the 3 came from. Well, there's another 3 over here, which is totally separate. Okay, so with that thought, I make this cosine, I make x plus 3 divided by square root of 12 cosine t. I make y divided by the square root of 12 plus 12 divided by 7 sine t. And then all I got to do is solve for x and y, and those are my parameterizations. My parameterization for x is minus 3 plus the square root of 12 cosine t. My parameterization for y is the square root of 12 over 7 sine t. I know that those will algebraically solve the given quadratic equation, right? So it'll be a parameterization of the path. The only thing that remains is to check on the direction and to choose a parameter domain so that it actually hits the part I want it to. There I have to think, personally, I have to think to be careful about the graph. So the ellipse looks something like this, right? And if you plug in t equals to 0, you get that point, right? Because t equal to 0 gives me what? It gives me minus root 3 plus root 12, minus 3 plus root 12, and then 0, so that's that point, right? If you put in t equals pi over 2 into these formulas, you get minus 3 and then the square root of 12 over 7, which is up here. When you put in pi, this is 0 again. That's minus 3 minus root 12, which is over here. And so you can see that you're going counterclockwise, right? Of course, you should have already known that because this is, again, like this problem. We already know if we put cosine sine, like similarly, it goes counterclockwise. So it's really no surprise that it goes counterclockwise. I was expecting that. I'm just checking on it, okay? Now, once that's determined, I asked the other section, you know, what parameter range should we choose? And they already told me this. I'm sorry I've deprived you guys of the chance to prove your test your might, prove your worth. Sorry about that. We'll play Mortal Math Combat some other day. But so there's pi less than t less than 2 pi. That makes me go from here to here. The endpoints are not included because you notice I said y less than 0, which means I want to avoid y equals to 0. Y equals to 0 happens at pi and 2 pi, right? So I want to omit those points if I'm going to be careful with that. And it is counterclockwise, like that. Assuming you know what counterclockwise means. Sorry, well, it's like that. Which I would add is a direction, in the same sense that left or right is a direction. Just saying. Sorry, if you're in my physics, there's this comment in the lab book that still is under my skin about there being a difference between right and left and counterclockwise and clockwise. I just find it to be an absolute absurdity. It's very troubling to me. That's why I can't teach physics lab. Reading that lab book makes me angry. You wouldn't like me when I'm angry. What's that? Makes you angry too? No, it doesn't make me angry. It just makes me sad. Sad that you spent $100 for it. But let's see here. Although, I mean, we've done our best to get the cost down. It just, you know, with the, I don't know, there's nothing to do about it. Except write a lab book, but that's just boring. Or to quote my son, boring. Anyway, any questions about this? So we have a little bit of time left to talk about problems from the book then. I hope that's enough to get you started. The homework which I said was due Monday, I'm going to make due Tuesday. That way you have Monday still to ask me questions about it. It has to be due Tuesday because then I don't know if the grader will get it graded before the test or not. That may or may not happen, who knows, right? Depends on whether the grader's got too much going on next week. But the grader should hopefully have the homework you already turned in this week back to you, probably Monday if I had to guess, maybe Tuesday, probably Tuesday. And I should have solutions anyway up for all the homework by hopefully Tuesday. I think I'm going to try to do it. I'm a little bit behind at the moment as far as your solutions go, but I will catch up. Any questions? Yes, sir.
So this one over here, ESDT.
Yeah.
So is velocity equal to the rate of speed over time?
That is true. V is equal to dsdt, where V is the magnitude of the velocity. So this V is the square root of, V dot V, which in terms of a specific formula is dx dt squared plus dy dt squared. Why do I keep writing with this marker? It's worthless. Okay, so somebody had a question about this homework problem. This is number 25 in section 10.4. Let me just try to explain to you the mysteries of this problem. You're asked to find the area inside this and that. Well, to find an integral representation of this. This is number 25. It's an odd problem, right? It's no secret. So I'm going to explain the answer in the back of the book to you, okay? So if you study the curve r equals sine theta, it's this circle here, right? It's the circle centered at 0, 1/2 with radius 1/2. It's the dotted circle. See that? Now this guy is a cardioid. If you study it going from 1 to pi over 2, it goes from this point back to 0 again. And then from pi over 2 to pi, it goes back to r equals to 1. That's this hump. And then from pi to 3 pi over 2, it goes to radius 2, like that. And then from 3 pi over 2 to 2 pi, it goes back to 0. Well, excuse me, it goes back to 1 here. Here's 2 pi, right? This right here would be this leg, all right? So there's the graph. The question is, what is the region inside these two curves? Well, it's going to be this part, right, and that part. You can show, I'll leave this to you guys, that these two intersect at pi over 6. I mean, you can check that it's true. If you plug in pi over 6 here, you get 1 minus 1/2, which is 1/2. Plug in pi over 6 here, you get 1/2. 1/2 equals 1/2. Seems reasonable. Unless halves disagree, right? So, no, I mean, halves usually agree. Except in marriage. But these halves aren't married, they're the same half. So it's more like 2 electrons or something, right? That's here. I'm sorry, I digress. Okay, so the picture is something like this, and you're asked to find the area. The key here, though, is to set up the area integral, you have to think about what's the inner radius, what's the outer radius. And it's not like 1 minus the other squared. That's not what's going on here. The inner radius is 0. You can draw a ray from the origin out to these curves at every point in this, like this petal here. And the same is true over here. By symmetry, if I can calculate the area of that piece and double it, that should give me the area, right? But so to get the red curve, I'm down here, right? The outer radius for the red curve is given by sine theta for the red area. But the outer radius for the black area up here is given by 1 minus sine theta. So the 1 minus sine theta is good from like pi over 6, right? All the way over to pi over 2. So that's why I integrate from pi over 6 to pi over 2 to get the area of this piece up here. All right? And to get the area down here, I integrate from 0 to pi over 6 of 1/2 sine squared theta, because that gives me that area. And then I just double it, and that's how you get the whole area. Does that make sense? So some students in the earlier section were confused about this problem. So the answer in the back of the book seemed mystical to them. So there it is. It's number 25. Number 25 from section 10.4. Another example I thought was useful to look at was this number 9 from 10.4. Supposed to find the area between r equals cosine theta and r equals 2 cosine theta between the rays theta equals to 0 and theta equals to pi over 4. It's a really pretty problem. So cosine theta, I will graph that one first of all, the rays, theta equal to 0, theta equals to pi over 4. And I really think that when the book uses this terminology, they are not allowing negative radius. I don't believe that they're allowing. It's irrelevant here because these curves are totally where, there's the curves in question don't, there would be ambiguity, I suppose, if these circles weren't just here, if they ended up being over here. So it's kind of, we can't really search the heart of the writers of the problem, whether or not they really were thinking about negative radius or not. So whatever, I should shut up about that. Still kind of bitter about it, though. I'll get over it eventually when I stop teaching calculus 2. So I got one more semester of strife. Let's see here. I'm just kidding. Let's see here. Cosine theta. This one, if you multiply by r, you get r squared equals r cosine theta, right? Which is x squared plus y squared equals to x. You complete the square, you've got x plus 1/2 quantity squared plus y squared equals to 1/4. That's this circle. This red circle, which is centered at 1/2 and has radius 1/2. Now, I'm not sure that you absolutely need to complete the square to see this. Like, I think you can plug in points into this and see this as well, because if you put in 0, you get 1, right? And if you just kind of follow cosine from 0 to pi over 2, it goes, it goes like this. At pi over 2, it goes back to 0. And I think if you do that, if you plug in a couple points, you can kind of see that it's a half a circle, and you can guess that it looks like this, right? So I'm not absolutely sold on the fact that you have to do this, but it is comforting to do this to be sure that that's a circle and that you're not missing something, right? Yeah.
That sine theta is basically that on the y-axis. So that it should be altered 90 degrees, so that would make sense.
Oh, sure. Yeah, if you already have in your mind that r equals sine theta is the circle up here, and then cosine theta is just related to sine theta by a shift of angle, then geometry demands that it be this. I'm so very happy with that line of thinking. I can't express to you how happy I am with that line of thinking. That is totally allowed. It's just not something I would put on other people. So I will refer to you the comments that were told to me in my college algebra class. Yes, James, you can do it that way if you'd like, but we're going to do it this way. So it's like, okay, thanks. Sorry. I know how it feels. I know the feeling. I'm just trying to tell you. All right. R equals 2 cosine theta. Well, that starts at 2. And as theta goes from 0 to pi over 2, it also goes back to 0, right? But when it gets to pi over 4, it's further out, right? It's like 2 over root 2. And again, you can complete this. We can multiply by r and complete the square, and you'll see that it's in fact a circle centered at 1, 0 with radius 1. So it's like this big black circle I haven't entirely drawn. And so these circles are kind of like nested, right? But they're tangent, or maybe that's cotangent. I don't know what that's called, but this red circle's inscribed anyway, right? And like that. I'm not sure what this is. There's got to be some kind of like agreed upon official geometric name for circles that are situated like this, but whatever. Anyway, once you do that, it's clear what area is being asked about, right? It's this area. And then you just go, okay, so integral of 1/2, integral from 0 to pi over 4, outer radius squared minus inner radius squared, and we do it. This gives me 3 cosine squared theta. I pull the 3 out. Half angle, 3/4, 1 plus cosine 2 theta. That integrates to theta plus 1/2 sine 2 theta. Evaluate from 0 to pi over 4. We get 3/4 pi over 4 plus 1/2 sine pi over 2, which otherwise known as 1, which gives us 3/4 pi over 4 plus 1/2, which, by the way, is 3 pi over 16 plus 3/8, which is the answer in the back of the book. Sorry, I was going through the unexciting part somewhat fast. But this is just integration, right, which we know how to do, and we will do with perfect accuracy on the final, right? Okay. Just assume that everyone can do perfect integration on the final. Don't even test on it. Yes, that's a. Just, I should just test you on the writing of your name, right? Like you'll get to the final, I'll be like, all right, let's arrange our chairs in a circle and let's talk about the grade we deserve in this course. And each of you can tell me about your mathematical, like your background and, who hurt you mathematically in the past. We can, air our grievances and find our inner, yes. What's that? Find our what? Inner self-worth, yes. Of course, yes. But probably I'll just give you a final and ask you to calculate a bunch of stuff. Yeah. So I'm saying there's a chance. That's funny. All right, so any questions? We could leave now and you could ask me questions Monday. How would that sound? Okay, let's do that.